differential equations. Specifically, we are going to talk about growth and decay. Real quick before we begin the lesson, growth and decay is something that you have been introduced to in Algebra 2, I think, or Algebra 1, I don't remember. Do you recall the equation for growth and decay is?
Not really.
Okay. The equation for growth and decay is equal to that. You probably might have seen it like this. That. So this right here, this was an equation that you were introduced to in like Algebra 2-ish. This is the growth and decay equation. And then graphically, if you remember, hopefully, growth and decay look like the equation that looks like that. That would be a growth. Versus decay would look something like that. Do you guys remember that?
Yep.
Okay, perfect. What we're going to do is basically the calculus that allows you to come up with this equation. Okay? All right. So the first thing I need to make sure you can do before we can get there is you got to be able to do some calculus. So we're going to talk about something known as the separation of variables. Okay. Separation of variables is literally what it sounds. You're going to separate variables in order to utilize your skills from calculus to solve a differential equation. So let's start out with a very easy, basic, baby differential equation. I can say solve the following. Y prime is equal to 7x divided by y. Okay. To solve means to find y equals. That's what it means. So we need to get rid of the derivative. Okay. Recall that y prime is the same thing as dy over dx. So if I rewrite it as dy over dx, then what I have is the following. Okay. Here is where the skill of separation of variable takes place. You need to get dy with all of the y variables and dx with all of the x variables on separate sides of the equal sign. So I chose this problem because it should be very obvious that all I have to do is cross multiply, and this would give me 7x dx is equal to y dy. What you just did is you successfully separated the variables. Each variable is with their corresponding variable. Now to solve the equation, you have to use your knowledge of antiderivatives. Okay, so this should be easy. The integral of 7x would be 7x squared divided by 2 plus some constant. And the integral of y would be y squared divided by 2 plus another constant. Question for you. Are these constants the same?
No.
No. So be careful with the operations. You can call this C1 and you can call that C2. But ultimately, here's what I typically do, and you're welcome to do this. I like to combine those two. So what I'm going to say is that 7x squared divided by 2 plus c is equal to y squared over 2. In other words, what I'm trying to say is as long as you have one constant of integration, you're going to be okay. Are we okay with what just happened? So now all I got to do is solve for y. So I'm going to multiply both sides by 2. So that gives me 7x squared plus c is equal to y. Now, some of you might ask, like, why didn't you multiply the 2 with the c? Well, doesn't 2 times c just produce another constant? So that's why I'm keeping it as a constant. Okay? But lastly, to solve for y, what are you going to have to do?
Square root.
Now, here's a question that I typically get. Should that c be inside of the root or outside of the root?
Inside.
Inside. So that means that your final answer would be this, and this is known as the general solution. Now it's the general solution because we can have different values for C. Okay? How would I get values for C?
If you have a point.
If you had a point. Now we've already done that in this class, so I don't think we need to practice, but if you had a point, you will utilize the point so that you can get a particular solution. Are you guys with me?
Yes, sir.
So then my question is, and again, I like to run this class based on feedback. What I tried to show you here was the concept of separation of variables. Do you understand what it means to use separation of variables?
Yeah.
Okay, so then
Yes.
follow-up question is, would you like to do another example, or are you okay with the example that we've done? Let's do another one. Perfect. All right, again, I like to run this class with feedback, so I'll do whatever you guys need. Okay, let's do another example. So once again, the instructions are going to be to solve the differential equation. So we're going to solve the differential equation, and the differential equation that I'm going to give you would be 3y prime plus y prime times x minus 6x squared y is equal to 0. Okay. What strategy am I going to use? Well, it's called separation of variables. Okay. Here's the thing. On the previous one, obviously, I gave you a very easy one where it was just one y prime. Right now, you have two y primes, so I'm going to have to do a little bit of algebra. Okay. Everything I'm about to do is algebra. So if you have a question, let me know. My first step is I need to get y prime by itself. So what I'm going to do is I'm going to get this y prime with the 3, and then this y prime with the x on one side. And then this term that does not have a y prime, I'm going to leave it on the other side. Okay? The reason why I want to do that is because if I have y prime on this side and on both of those terms, then I can successfully factor out a y prime, and then I would have a 3 plus x left. Which then I'm allowed to replace y prime with dy over dx, and then I would have times 3 plus x is equal to 6x squared y. Once I have just one y prime left, and now I can separate the variables. I need to get x on one side and y on one side, so I need to take this dx to the other side by multiplication. So that leaves me with dy 3 plus x is equal to 6x squared dx. Agreed? Now, I need x's with x's and y's with y, which means I'm going to have to divide this by y, which means I have to divide this by y. But I got to divide this one by 3 plus x, and I got to divide this one by 3 plus x. So by doing so, this cancels out, and it leaves me with 1 divided by y dy, and on the other side, the y's cancel, and that leaves me with 6x squared divided by 3 plus x dx. Right? And I just realized I made a mistake. Let's see, did I make a mistake somewhere? Yes, I did. I wrote down the problem wrong, because right now this is not, you're not going to be able to integrate that. That's my fault.
X and x power 3.
I'm sorry. This right here is supposed to be x to the power of 3. That was my fault. So that's x to the power of 3. That's x to the power of 3. X to the power of 3. To the power of 3. To the power of 3. That was my fault. I just miswrote the problem. My apologies. Okay? Alright. So here's my question then. Have you successfully separated the variables?
Yes.
So now that you've separated the variables, what are you going to have to do to solve?
Integrate.
Integrate both the left and the right hand side. So we're going to integrate that side and we're going to integrate that side. The left side is very easy. What is the integral of 1 over y?
Natural log of y.
Very good. So it's a natural log of y. I'm not going to put a plus c because I'm just going to put the plus c on the right side. Okay? All right, now what about this side? I have 6x squared divided by 3 plus x cubed. Is that integral?
Get out 2 out of the integral, because 3 plus x in exponent 3, differential of it will be equal to the 3 times x in exponent 2. So we can use the rule that integral out of dx divided by x will equal to like a natural logarithm.
Very, very good, Stepan. Notice that if I factor out a 2, I'm left with a 3x squared. The derivative of the denominator is 3x squared. So if the derivative of the denominator appears on the numerator, that's going to be a natural log. So that means that the integral of the right-hand side is going to be 2 times the natural log of 3 plus x to the third power. And then I'm going to add my plus c. Are we okay? All right. I'm going to solve for y. So what I'm going to do is I'm going to take one little step algebraically. Hopefully you haven't forgotten this. So let me take it and let's see if you understand what I did. So I'm going to do ln of y, and then I'm going to rewrite this as ln of that. Any questions as to why I did that, or why I'm able to do that? Perfect. By the power property of logarithms, I made it a power. I also got rid of the absolute value because anything squared is going to be positive, so the absolute value is not necessary. Okay? So now, how do I solve for y?
You can take out logarithms because all natural logarithms is exponent of same base, so same base of e.
Unfortunately, I have that plus c though, so I can't just take out the logarithms. So my question is, how can I get rid of a logarithm? Specifically, a natural log.
You put in the exponent and have the basis e.
Very good.
Able to cancel out.
So I'm going to do e to the power of that, and then e to the power of all of that. Okay? What's e to the power of ln of y? Well, that cancels and it leaves you with y, right? And then what is e to the power of all of that? Well, this is where you're going to have to be careful. You can't just cancel this because you have the plus c. So the more algebra you know, the easier this becomes. What I'm going to do is I'm going to break this into two things. I'm going to make this into e to the power of natural log of 3 plus x cubed squared multiplied by e to the power of c. Why?
Oh, and we can use e of power c like a older c because there's
exactly. Very good. Good observation, Stepan. Let me make sure I didn't lose anyone. Do you guys understand that when you have addition on the exponents, you can break that up into a multiplication of the base with the exponents that are corresponding next to the addition? So that's why I'm able to break this up into multiplication. And just like Stepan said, e to the c is just a constant, so I'm just going to leave it as a constant. So doesn't this then technically become some constant, and then e to the ln cancels, leaving you with c times 3 plus x cubed squared as a final answer? Yes? No? Questions? Yes.
So, can you explain again why the e to the c just becomes?
Yeah. So E is approximately like 2.71-ish, right? And then that's just a constant, right? So if you have a number to a constant, it's just going to give you another constant, right? And since I still don't know what the constant is, I get to call it whatever I want. So I'm just calling it C. But if you wanted to, you can switch it. Some people like to switch it so because they don't want to get confused. So you can call it whatever you want as long as it's a constant. Like some people can call it K, some people call it A, some people call it B. I'm just staying consistent and keeping a constant, a C for constant. Okay? Cool. All right. Good question. Anything else?
So the answer should be 3 plus x to the cube squared times c, right?
Correct. Times C. Yeah, so in other words, you got a multiplier here in the front of this. Questions about, I think you guys understand the separation of variables. I think that's not going to be very difficult in my opinion. Where I can see some of you guys struggling is it's the algebra. I think the calculus is going to be fine for most of you guys. Whatever integration you run into, you definitely have the skills to integrate. Okay. Don't forget to think about U substitution. That's typically that should be your #1 strategy to think of prior for any integration before you try anything else. Okay. All right. Questions about this problem before we move on? Perfect. Okay. So then now that you know separation of variable, now we can go back to basically the title of this, which was growth and decay. So we have growth and decay. So you have that formula, or that formula was just given to you. So the question really is, where did that formula come from? And that formula comes from the following differential equation. That. Now, I want to take this differential equation and I want to break it down into actual language. I need you to understand what this says, okay? Can anybody translate this into English for me? What does this say?
The slope is low.
Okay, this is the slope. Good. Now, slope would be a rate of change. Do you guys understand that? Yes? So this says the rate of change of y, right? Because it's of y, it's the derivative of y. Equal sign means is. Now, what is happening between these two? Operation-wise.
They multiply.
Multiply. Now, I think you've heard this vocabulary before, but let me write it. What I'm going to say is the rate of change of y is directly proportional to k. When you see the word directly proportional, it means that you are multiplying by whatever's here. So in this case, it's by k. So what this is saying is the rate of change of the y is directly proportional to k, so that means it's y times k. So when I see this statement, I'm going to say, okay, the rate of change of y, so it's going to be dy over dx, it's equal to directly proportional to k, or that's got to be k times whatever variable you have up here, which in this case was y. Okay? So, how do we solve this differential equation? What do you think? How do I solve it?
Separation of variables.
Cool. So, separation of variables would give me dy on one side, and it would give me dx on the other, right? Where is everything go? Tell me, what do I have with the dy?
1 over y.
1 over y. And what do I have with the dx?
K dx.
K dx. Once you separate the variables, what do you do?
Integrate.
Fantastic. And hopefully you look at both of this and you're like, this is a very easy integration. Integral of 1 over y dy is equal to the natural log of y. What's the integral of k with respect to x?
Kx.
Kx. And now remember, this is indefinite integration, so they're supposed to have a plus c. I'm deciding to just combine them both in one side. Cool? So how do I solve for y now?
Like what we did on the last problem.
Cool. E to the power of that, and then e to the power of all that. So on the left-hand side, that cancels, leaving you with y. Now, if I have e to the kx plus c, what I have is e to the kx multiplied by e to the c, right? And then we can all agree, or hopefully you understood that from earlier, e to the c is just going to be another constant, so that's just going to give me c e to the kx, which is the growth and decay formula that you learned back in Algebra 2. Yes? No? So, I have a question for you. Let's say I tell you to solve the following differential equation, and I tell you that dy over dt, I'm going to switch the variable, is equal to 20y. Could you solve that without actually doing any calculus for me?
we can just plug in.
Yep. This is going to be y equals what?
C e to the power of 20x.
I'm going to use t in this case, so make sure you follow the vote, okay? So what I'm trying to say, guys, is any differential equation that has this form right here, any differential equation that has this form right there, you should be able to recognize and say, oh, wait a second, that's growth and decay, which means I can automatically go to growth and decay. The number here is k, and that if we have a 20 here, then that means there has to be a 20 there. Cool. If there was a -5 here, then that has to be a -5 there. You guys with me? But I'm going to be honest with you. Is it really difficult to solve this differential equation?
No.
No. So even if you don't make that distinction, you should be able to solve that differential equation relatively easily. What I'm trying to say is that you could save some time if you recognize it. Are we okay with my point, or the point that I was trying to make there? Yes, no? Talk to me, people.
Yep.
Fantastic. All right. So then I do have a question for you, and once again, I'll do whatever you guys want me to do. This is your class. You have a voice in my class. Have you done growth and decay problems before on your own, like in other classes?
Yes.
Yes.
So do you need me to give you an example, or are we okay?
I think I'm okay.
Okay. Does anyone want me to do an example?
It's been a minute since Algebra 2, so I think an example would help.
Okay. Fair enough. I'm with you, man.
Angry?
Okay, let me pull up an example real quick because I didn't have one ready. That was my fault for not being ready. Let me pull one up, and then I'll write it down. So let me go ahead and, are we okay with this page? Can I remove this page from the screen? Okay. So let's say I have something like this. All right, I got something on the chat. Okay, so we do one example. All right, so there we go. Let me see what do I got here. Let's do some growth and decay problems. All right. Example. The population of a country in 2011 is given below. Okay, so here's what we got. In 2011, we had a population of 98.3 million. Okay? If the rate of growth is 0.021, write a differential equation that represents the population. Okay. So the population in 2011 is given below. So it's 98.3 million. If the rate of growth is 0.021, by the way, this is going to be multiple parts. Part A would be, what is a differential equation that represents the population? Anybody want to give it a shot?
Would it not just be the dy over dx is equal to ky, with that k being the population growth?
Fantastic. dy over dx is equal to 0.021 what? Y. Fantastic. That's an easy part for you. You have to be able to come up with the differential equation. Okay? Now, solve the differential equation. So how would I solve the differential equation? Can anybody explain what this is? Well, by the way, instead of x, I think we should be using t. Can you guys explain to me why t instead of x?
Because it's time.
Time. So can you guys explain what dy over dt means?
Slope.
The change in the rate of growth over time.
Change of population over time. Which, by the way, what is y? So y would represent what?
The population.
The population. Which, by the way, these are variables we chose. Like, for example, you could have said dp over dt so that you can use p for population. But we chose y, it's fine. And then t is time, right? Specifically based on the graph, well, we'll talk about that here in just a second. It's going to be in years. Do you understand why? Not on the graph, based on the problem. So I don't know why I said graph. Because I talked about the population in the year 2011, so it makes sense that the time would be in years. Okay? So now, how would I solve that differential equation?
Wouldn't it just be like y is equal to ce to the power of 0.021 t?
Perfect. Yes? Do you understand why I was able to do that without having to do any calculus?
Yep.
Now, could I have separated the variables and solved for it?
Yeah.
Yeah, we could have, but there you go. There's your model. Now, so that's part, I don't know, part A, part B. Now, part C. If we let the year 2010 represent t equals 0, find a model to represent the population at any time. So, if we let the year the year 2010 represent 0, find a model that would represent that. So what do I do? How do I figure that out? Because I have this model here, but it's not a complete model because I need to know what C is. So what do you guys think? This is where basically, this is going back to algebra 2. Okay? How would you solve this?
Your y would be that 98.3 million.
So
and then-
98.3
and
is
for t would be 1 because 2011 is 1 year after.
exactly. So we're going to say C is equal to 0.021 times 1. Agreed? Now this is going to require a calculator, so let me grab one real quick. Alright, so how would I solve for C in this case, by the way? Because I would expect you to show work.
You would do. Oh wait, I don't know.
Well, isn't this right here just going to be a number?
So we can calculate this like a number as this find C. After we find C, we can use it in all the formulas to calculate the answer.
Absolutely. So it's just basically, it's going to be divided by e to the 0.021, right? Everyone okay with what I'm doing there? So now, I'm going to do an approximation because I'm going to use a calculator. So I'm going to go ahead and pull out my calculator, and I'm going to do a division. So we got 98.3 divided by e to the power of 0.021. I know you can't really see that, but that's what I typed there. There you go. I'm going to hit enter. And I got 96.257, blah, blah, blah. So I'm going to use 3 decimals. So 96.257. So what is the model that represents this population?
Y equals 96.257 times e to the 0.021 times t.
Fantastic. And finally, if I ask you, what is the population in the year 2020? How are you going to figure that out? You're going to plug. So So you're going to plug in 10 for t, right? Because if 2010 represents the year 0, then 2020 would be represented by t of 10, right? And then you would use a calculator for that. Agreed?
Yes, sir.
All right. So does this bring back memories from Algebra 2? Are we okay with that second part? Like, these are what the problems look like as far as, like, once you're done with the calculus, everything goes back to algebra. Cool?
Mr. K, how would you separate the variables if it's only one variable?
Okay, so on this one, so I'll go ahead and do the calculus right here. I would put y on the left side by division, so I'm going to do 1 over y dy. And now 0.021, to make my life easy, instead of bringing it with the y, I'm just going to leave it on the other side. So I'm going to leave it as 0.021, and then I'll have the dt on that side. Now, that choice was just to make my life easy. You can bring the 0.021 with you if you like. And then after that, we're going to integrate. So this gives you ln of y, and then this gives you 0.021t plus c. You do e to the power on those two parts, so that gives you that, cancels that. Now, when you have this, that's going to be e to this power times e to that power. E to the power of c is just a constant, so that's how you're able to just get c times e to the 0.021t, which is the same thing as what we had earlier.
Thank you.
You're welcome. Good question. Any other questions about growth or decay, guys? You know, part of the problem might require some calculus like this one, but once you're done with the calculus and you're able to come up, or if you recognize, which is, I think that's the way we went about it without doing any calculus, if you recognize that that's growth and decay, then you're able to come up with the equation relatively quickly. And to be honest with you, after that, everything is just algebra. You just got to go back and, you know, use the information that was given so that you can figure out what C is and you can come up with your model. Okay? Isn't that nice that now you know where that formula comes from? Well, I mean, I don't know. I'm a math nerd, so sometimes just me giving formulas kind of bothers me. So now that I know where it comes from, it makes me feel a little better. Okay? All right. Questions about growth or decay, y'all? Perfect. All right. So the next thing we got going on, guys, is on 6.2, there's one more thing about growth and decay that I'm going to be honest with you. I'm not really sure why we have it on the Calculus BC exam, but I'm going to teach it to you because it's obviously on the AP exam. It's called Newton's law of cooling. So Newton's law of cooling. All right. Well, obviously I know why it's in here, right? I mean, we're going to use calculus to figure this out, but I feel like this has more application in your physics class. But anyways, all right. Does anyone know Newton's law of cooling, by the way? Okay, I'll take that as a no.
It's how heat transfers, right?
Yeah, it's how heat transfers, basically. Okay. All right. I know, like, the conversation about heat it goes way more, right? It's more than what it sounds.
A lot of different formulas that you need to remember, but my favorite is Gay-Lussac law.
Yes. So temperature is actually a lot more complicated than what people think of. So that no one gets scared, we're not gonna go as in depth as if you were taking physics, right? If you take physics, you obviously take a couple weeks to really study temperature and heat transfer and all kinds of stuff. Okay, we're not going on that direction. Okay. Really what this is about, guys, is it's really what it sounds like, okay? Newton observed how temperatures change between objects. So let me give you an example of what I guess his thought process was, and then we'll talk about the mathematics. For example, currently, well, today's kind of a sunny day, so I don't know how cold it is outside. I haven't been there in a while. But, you know, the last couple days been relatively cold, right? So currently I'm in my room, and I think the temperature in my classroom right now, I have it like at 73, okay? I'm comfortable. Perfect. So would you say then that my body temperature is going to be close to 73 degrees Fahrenheit? Yes or no?
No.
No.
Why not?
Because I've been to a hospital and it says my body temperature is 98 degrees.
Okay. Why is my temperature not reaching that?
homeostasis.
Oh, it's yeah.
No, because like outside, we have air touching us, so we cooling down all the time. That's why we eating,
Right.
like walking, so we get energy from that.
So we can get like really biology, very physics here, but really my body's not gonna reach that temperature because my body's protecting me, right? Yes, my body needs to be at a certain temperature. I hope you guys know that, right?
Maybe.
Yes, and we're not gonna dive into the biology of that, right? Because I gotta be honest, I'm terrible at that. I know there's some of you guys that are probably great at biology, so you know way more about that. But my body basically protects, my mass, my muscle, everything, the fat in my body keeps my body at a certain temperature. However, does the temperature around me, is that gonna affect the temperature of my body?
Yes.
Yes, right now, right? So like if I were to go and you feel this every time, like hopefully you feel this, hopefully, right? If it's very cold outside, your body automatically feels it, and your body temperature begins to drop. Agreed? And if it drops too much, then that's you can develop hypothermia, etc., right? But here's the observation that you'd make. Doesn't your surroundings affect the temperature of, I guess, yourself, right? So would that be true for any object? Would the surrounding temperature affect the temperature of the object?
Yes.
Yes. So here's my question. If the surrounding temperature is cooler than the object, what is going to happen to the temperature of the object?
Decrease.
It will decrease. But if we have the opposite, if the surrounding temperature is greater than the temperature of the object, what's going to happen to the object? The temperature
Increase.
will increase. Fair enough? Like, is that like a fair observation? I just need to make sure everyone understands, like, before we get to the math. Like, that makes sense, right? If it's really hot outside and you go outside, your body temperature increases, right? If it's really cold outside and then you go outside, your body temperature will decrease, right? Because the surrounding temperature affects the temperature of an object. Cool? That's what Newton's law of cooling is. That was his observation. Okay? Now, he developed the mathematics for it. And here's what he came up with. He figured out that there was a differential equation. He figured out that the change in the temperature of an object with respect to time was equal to some constant. Okay? So we got some constant multiplied by the difference in the temperature of the object and the temperature of its surroundings. Okay, so let's label a few things. TO is object temperature. TS is surrounding temperature. Which, by the way, for the simplicity of this class, we're going to maintain constant. So in other words, we're going to have a controlled environment. Okay? And then K is just a constant. And then lowercase t would be time. Are we okay? And by the way, this is true for any method of measuring temperature, whether it's Celsius, whether it's Fahrenheit, Kelvin, okay? So, how would I solve this differential equation? I want to know what the temperature of the object is. How do I solve it?
You need to know constants that, like, what materials you use that provide, like, temperature provide.
Oh, you're going way beyond this class. No, we're just gonna keep it very basic. With very basic, guys. I promise. It's not gonna be very physics. I know, like in the real world, we think about material, etc., etc., etc. No, like right now, we're just gonna keep it basic. So in other words, this is the differential equation. I'm just asking you, mathematically speaking, how could I solve for TO, mathematically speaking? Think about what we've been doing today. What do I need to do?
So you need, do something with the x and y. You need to separate them.
Good. So I need to get dt TO on one side, and then I need to get DT on the other side, right? Now remember, this and this, they are going to be constants, which means that those are not variables. So the only variable on this side would be that. Yes? So I need to get TO to the other side by using what? Well, what's happening between these two? There's multiplication, so for me to get it to the other side, I need to divide. So this is going to be 1 divided by temperature of the object minus temperature of its surroundings. And I'm going to decide to keep this K on this side, just for simplicity. Okay? Have I successfully separated the variables?
Not really, there's TS.
But TS is what?
Oh, it's constant.
It's a
okay,
constant.
sorry.
So we are good. You with me? It's just a number. So we should be able to integrate. The right-hand side is relatively simple. What's the derivative of K with respect to T?
KT.
Good. So KT, and then I'm going to put the plus C on this side. Now this one, think about it. Again, my reminder to you is that the temperature of the surroundings, that's constant, so that's just a number. So this basically says T object minus a number. So what's the integral of that?
It will be a natural log of the absolute value of T naught minus TS.
Very good. Now, I want to solve this for TO, or temperature of the object. So what do I do?
You have to cancel out the logarithm, so you're going to put it as a base of E.
Cool. So on the left-hand side, I'm going to be left with temperature of the object minus temperature of its surroundings is equal to what?
E to the power of KT.
What about that plus C?
You can
E to
split
the power of
take it out.
KT times
C e to the KT, right? That's what's been happening today. Have you guys noticed that, right? Can I skip that middle step, or is anyone lost?
yeah, you can split it, I think.
Perfect. So now, this is perfect. I'll be honest, I have no problem with this, but if you really wanted to get picky, if you wanted an equation for the temperature of the object, then all I have to say is take that temperature of the surrounding to the other side. So that's going to be the temperature of an object is equal to the temperature of its surroundings plus C e to the KT. And this right here is Newton's law of cooling. Okay? Very simple. Do you notice that the second part, if you really just want to memorize this, do you realize that it's just basically saying, hey, take the temperature of your surroundings and then add growth or decay? That's really what it says. And it makes sense because growth or decay would be how much the temperature is growing or decaying. Cool?
So, on that AP test, what do we really have to know?
Good question. You have to know that if you see this, your answer would be this. However, if you don't remember it, can you on your own do all the calculus? Absolutely. So this is what I always tell my students every year. You're going to have a lot of things to memorize. So you don't really have to memorize this because you can solve it. I believe in your capabilities of integration, and so should you, hopefully. But if it's the opposite, where you're like, I don't think I can solve that, then unfortunately, my friend, you will probably have to memorize this. Okay? So then let's practice a problem. Okay? So if I'm telling you that an object follows, you know, Newton's law of cooling, so an example would be an object, whatever this object is, it doesn't matter, an object follows Newton's law of cooling. Cool. If the surrounding temperature is kept at, I don't know, let's make up a number, 60 degrees Fahrenheit. And the object is introduced to this environment at, I don't know, let's say 133 degrees Fahrenheit. And it cools to 100 degrees Fahrenheit in 15 minutes. How long will it take to reach a temperature of, I don't know, let's make something up, let's say 80 degrees Fahrenheit. Alright, so I'll let you catch up on writing that problem. So we've got an object that is originally 133 degrees Fahrenheit. We're going to introduce that object into a controlled environment that is kept at 60 degrees Fahrenheit. Okay? We made some observations that it cooled down to 100 degrees Fahrenheit in 15 minutes. So it went from 133 degrees Fahrenheit to 100 degrees Fahrenheit in 15 minutes. How long will it take for that object to reach a temperature of 80 degrees Fahrenheit? Okay, you have two options here. You then recognize that this is Newton's law of cooling, so that means that you know that the change in temperature of the object over time is equal to some constant times the temperature of the object minus the temperature of the surroundings, right? But you know the temperature of the surroundings. What's the temperature of the surrounding? 60 degrees. So you could start here and you can solve the differential equation. Agreed? Yes or no? Talk to me. Or you could already know that the solution to this is going to be what?
80 degrees.
Be careful. Well, hold on. Like the solution to this. Like after you integrate, what is it?
CE to the KT plus TS.
So, but don't you know what TS is?
Yeah, 60.
So couldn't we skip all the calculus and say that the temperature of the object is literally going to be 60 plus CE to the KT? Yes? No? Do we understand? Do we understand that if I do the calculus for this, it's basically like me repeating everything I did up here to just get down here. But I know that TS is the temperature of the surroundings, which is already given to me, which shows up both on the differential equation, but also on the solution. Yes? So now, that's what I have. I need to figure out a few things. I need to figure out what C is, and I need to figure out what K is in order for me to come up with a model. So how am I going to do that? The rest of this is not calculus. What is the rest of this? Just algebra. Okay? So you tell me, how can I use the information that was given to figure that out?
You could begin 15 for T, and then 100 for the object temperature.
Okay, so you're going to say 100 for the temperature is equal to 60 plus CE, and then what do I put for T?
15.
So that will be 15K. Well, we have an issue there because I have two unknowns, so I don't know how I can solve for any of those if I have two unknowns.
When t is equal to 0, isn't t 133?
Good. So I suggest that you start out with the initial. So 133 is equal to 60 plus CE to the 0 times K. Agreed?
Yeah.
So then that gives me 133 is equal to 60 plus C, which means C is equal to what?
73.
73. So now I can go back in to this expression that we have earlier. Instead of saying CE to the 15K, we can say 73 e to the 15K, right? So how do I solve that?
T is in 15, and then for TO you can put 100.
Right.
Solve for K.
Cool. So I'm going to subtract 60. Agreed? So 100 minus 60 gives me 40. And then I got to divide by 73, right? So that's going to give me 40 divided by 73 is equal to e to the 15k. How do I solve for k?
Natural log of 40 over 73.
So now I got the natural log of 40 divided by 73 is equal to 15k, which means k is equal to what? 1/15 of the natural log of 40 over 73. You guys with me? So what is my model? The temperature of the object is going to be what? What's the model?
Plus 73 e to the whatever we just had, 1/15 natural log of 40 divided by 73 t.
Times t. Now, the reason why I didn't use my calculator here is because you don't want to round in the middle of the problem, so you should be perfectly okay with just putting this there. Are we okay with that? If you were in Algebra 2, I would probably let you round, but you guys are in Calculus, I think you guys can keep up with just coming up with that expression, right? So now that you have this expression, how are you going to answer the question? It says, how long will it take for the temperature to reach 80 degrees Fahrenheit?
80 for TO.
Exactly.
And then you just do that process all over again.
Fantastic. So now we have 80 is equal to 60 plus 73 e to the 1/15 ln 40 73 and then t. Agreed? Do you need my help solving this, or are we good? I would subtract 60, so that gives me 20. I would divide by 73, so that gives me 20 over 73 is equal to e to the power of 1/15 ln 40 over 73 and then t. I would take the ln of both sides, so that would give me ln 20 over 73 is equal to 1/15 ln 40 over 73 t. So to solve for t, I'm going to divide everything by 1/15 ln 40 73. So t would be approximately, if I use my calculator, this is where I would use my calculator. I'm going to say the natural log of 20 divided by 73 divided by 1/15 natural log of 40 over 73, and I got 32.283. And what would be my unit of time?
Minutes.
Minutes. So it would take 32 minutes, about 32 minutes, right? From where? After the 15 minutes or from the moment this object was introduced to the surroundings?
From the moment it was introduced.
Exactly. One thing you want to be careful on the AP exam is sometimes they word things differently. So for example, one way I saw it 1 year was like, how much longer did it take? So if it said how much longer, what would you have to do?
Subtract that by 15.
Subtract the 15. So then it would be 17 minutes, 17.283 minutes. Okay? So please just pay attention to the wording of a problem. Okay?
Zakaria,
Yes, sir.
can you explain how you got that equation ln of 20 over 73 again?
Yeah, for sure, dude. So over here, like this is the equation that I was trying to solve. So I subtracted 60. So 80 minus 60 gives you 20, right? And then I divided by 73. So that's how I got 20 over 73 equals e, and then all of that mess, right? To get rid of this e, you got to take the natural log. So you're going to do it to both sides. So I did ln of 20 over 73. And then if I do the ln on that side, it cancels the e, and it just leaves you with the 1/15 ln 40 over 73t. Cool? And then to solve for t, since all of these things are being multiplied, you're just going to divide both sides by all of this. So this would be gone. So that means t would be ln 20 over 73 divided by 1/15 ln 40 over 73. And then I use the calculator afterwards.
Right, so if you use ln, ln means log e, right?
Logarithm base e, yes.
Oh,
Yeah, so ln is the same thing as a log base e. So when the base, in this case, since I was doing log base e of e to the 1/15th ln 4073t, because these two things are the same, by the power property, since this is a power, it goes all the way in the front, and then log base e of e is 1, so all of that times 1 is it's itself. Good question, man. And this, I mean, again, like, this live sessions are for that. You can ask me, I mean, if you get stuck on something, just let me know. Okay? Any other questions, guys? Are we good? All right, so as far as 6.2 goes, this is it. Okay? By the way, I didn't tell you, but that was 6.3 as well. So what you've done is you've been able to do 6.2 and 6.3. 6.3, because I'm not going to make a video over it, 6.3, guys, is completely separation of variables. Like, it just has a lot of practice on separation of variables. But with this video, do you think that was enough for you to understand separation of variables? Okay, I'm going to take that as a yes. So I'm going to go ahead and end the, I was doing a recording. Okay, so I'm going to go ahead and end the recording for this.